Good afternoon. This lecture concerns applications of electromagnetic induction under the guise of inductance. And so we're going to talk about topics like self-inductance, RL circuits, energy in a magnetic field, LC circuits, and RLC circuits over the course of probably these two lectures. There are plenty of applications of electromagnetism and electromagnetic induction, as you'll see. We'll start with a really simple one. That's called self-induction. So Faraday's law tells us that changing magnetic fluxes can induce electric currents. Let's watch this simple example of self-induction. Watch what happens. Suppose I have a circuit, a very simple circuit with a battery, and a resistor, and a switch. Now nothing's happening at all when the switch is open. But let's say I close the switch. So when I close the switch, that's going to cause a current to flow in that direction and around the circuit. However, that current is going to cause a magnetic field. As you can see, these curly lines are curling around the wire. This magnetic field, of course, indicates that we're getting a change in magnetic flux, and nature wants to oppose that change in magnetic flux by Lenz's law. And so what it's going to do is it's going to cause what we call a back EMF, an opposing EMF, to resist this change in magnetic flux. Now, it's not going to be very large, and it's not going to be for very long. As you know, anytime you turn a switch on, it almost looks instantaneous, that the lights go on or something else happens. In fact, there is a very, very almost imperceptible time delay because of this self-inductance in the circuit. So what's going to happen is this back EMF, or self-induced EMF, we call E sub L. And I'm going to define that as minus a constant I'm going to call L, which is the inductance in the circuit, times di dt. So in other words, this back EMF is proportional to the rate of change, time rate of change of the current. L, as you'll see, will remind us a bit of capacitance in that it's not a physical quantity so much as a geometrical quantity. And we'll show this with an example of a solenoid. In fact, Faraday's law, let's talk about this. Faraday's law tells us that my back EMF, or my induced EMF, is going to be equal to minus n times the derivative of magnetic flux with respect to time. And so if I can look at these two expressions and equate the two, I notice that I got a dt on both sides. I can integrate both sides, and lo and behold, I have a very nice expression for inductance, which gives me L is equal to N phi divided by I. So this is a very nice, simple expression for the inductance in a circuit. We can also write L as equal to minus E sub L divided by di dt, an equivalent expression for L. Units of inductance called the Henry, after Joseph Henry, the one who independently discovered electromagnetism along with Faraday. The Henry is defined as 1 volt second per amp. So inductance is essentially, it's a measure of the opposition to a change in current. Let's do an example of this. Let's find the inductance of a solenoid of length L with a number of turns, capital N, and a constant current I going through it. So here's my solenoid. It's a long solenoid. It'll have a length L. It's got N turns. and as we said, some current I going through it. Well, the first thing we have to do, if I'm going to use this equation to find the inductance, I need to calculate the flux, the magnetic flux of the solenoid. Well, so to find the magnetic flux, that's going to be equal to the integral of B dot dA for the solenoid. Now let's give the solenoid a cross-sectional area A. And so the field, if it's a constant current, the field for a solenoid is equal to mu naught times I times the number of turns divided by L. Therefore, the flux, in this case, because I is constant, everything else is constant, I have a constant integrating dA, which is just going to give me, when I take the integral, it's just going to give me the cross-sectional area A. So I can write this as mu naught times N times I divided by L times the area. So a very simple expression for the magnetic flux. And now what I can do is calculate the current immediately using this equation. So I find that the inductance then is N squared times mu naught times I. I's go away, right? I've got an I over an I, area divided by a length. And so you can see with this demonstration, look at the units here. There are no physical units. This is a number of turns, that's an area, that's a length. That's just a constant, a proportionality constant. So you can see inductance, like capacitance, is simply a geometrical factor. Okay, we could do an example, a very quick example of this. Suppose I have, so we'll do the following case. I have an inductor with 500 turns. I have a length of 1/10 of a meter and a cross-sectional area of 5 times 10 to the minus 4 square meters. That being the case, if I want to find the inductance, that's just going to be equal to mu naught times N squared times A over L. And that will give me, put all my numbers in, 1.57 times 10 to the minus 3 henries, or if you like, 1.57 millihenries. Okay, so that's a very simple example of finding the inductance of a solenoid. We could take it a step further. Suppose the current decreases at a rate of 20 amps per second. What is the induced EMF, or the back EMF in this circuit? So in that case, E sub L is going to be equal to L minus L dI/dt. So I can take my inductance here, multiply by the change in current with time, and I'll get a back EMF of 0.0314 volts. Okay, so that's another simple example of what we can do with self-inductance. Another interesting aspect of inductors is, let's look at a circuit that has a real inductor in it. In this case, we'll talk about RL circuits, that is to say, circuits that have resistors and inductors. So in this case, we have a configuration like so. It's a little bit more complicated than normal, but let's see how it plays out. So the circuit symbol for an inductor is a curly little, almost solenoid-shaped line. And I've got the following configuration, and I have two switches in the circuit. This we'll call S1, and this we'll call S2. That's point A and point B. And what I'm not going to do at least for now, is I'm not going to let both of these circuits, I should say, at the same time be open. So this is what we're going to do. If I have a solenoid or a coil in my circuit, that solenoid is going to prevent the current in the circuit from reaching its full value immediately. It will take some time to reach its full value. And so in other words, my circuit is going to be sluggish with regard to voltage changes, like when I engage the battery. So we call an RL circuit. So this switch, as I said before, can never be open. It's either connected to point A or point B. When it's connected in this way, we have we have a battery in the circuit when I connect S1, and now I'm using the battery to send a current through the circuit, and then later on I'm going to connect to point B, where it just becomes a circuit with no battery in it. So let's do the first part first. Let's close switch number 1, and then let the current flow through the system as such. Okay, that being the case, what's going to happen? Let's apply Kirchhoff's loop rule. So I have the voltage coming out of the battery minus the voltage dropped across the resistor minus the voltage dropped across the inductor is 0, right? So the sum of the voltages around the loop will be 0, Kirchhoff's loop rule. The simplest way to solve this differential equation is, let's do a change of variables. Let's let x equal E over R minus I. And therefore dx is going to be equal to minus di. That's going to give me a new differential equation, a simpler looking separable differential equation. We'll write it this way. X plus L over R dx dt is equal to 0. I can change variables, I should say I can separate variables, put the dx on one side, the dt on the other. When I do, I'm going to have the following situation: dx over x is equal to minus r over L dt. At that point, I'm going to integrate both sides. I'll integrate from x naught to x on this side. I'll integrate from 0 to t on this side. When I do that, and I integrate, I'm going to get log of x over x naught is equal to minus r over L times t. I exponentiate both sides, and when I do that, I get x is equal to x naught e to the minus r t over L, where x naught is equal to full current e over r. That means I can write e over r minus I as e over r times e to the minus r t over L. And now I finally have I as a function of t as e over r times 1 minus e to the minus t times r over L. Notice, this equation looks eerily similar to a charging capacitor. There's not a whole lot of difference except we're using inductance here rather than capacitance. And let's have a look at what happens. At t equals 0, this term becomes e to the 0 or 1. 1 minus 1 is 0, so the current in the circuit at t equals 0, I is equal to 0. As time goes on, this will become, as t approaches infinity or gets very large, 1 minus 1 is 0. So at large t, the current will approach E over R. So the circuit will have full current in it. So That makes sense. We call the ratio L over R is what we define as the inductive time constant T sub L or tau sub L. And when T is equal to tau sub L, just like in the case of the capacitor, we have the current in the circuit is 0.632 or 63.2% of the total current in the circuit. So it should remind you very, very much of a RC circuit, only we're using inductors instead of capacitors. Well, let's look at this a little bit more closely. Let's ask the question, how does the current change in time? I'm going to leave the second part of this diagram up because in a minute I'm going to move the switch over. But for now I'm going to say, what is di dt? Well, that's just going to be equal to E over L times E to the minus T over tau. So that's a time rate of current. The time rate of change tells me that at t equals 0, it will be 0, but it's going to fall off exponentially. So my change in current with time is going to become less and less and less and less. So let's look at the following. Now I've maximized the current in the circuit. So time has gotten large enough where 1 minus E